to the unit step function and the Laplace transform. So the idea here is so far, all of our forcing functions have been continuous, right? Otherwise, we were forced to just solve for a solution sort of within an interval of continuity. And so now our goal is to start to work with functions which are not continuous. So our goal is to find solutions over intervals where the forcing function has discontinuities. So we are going to focus on sort of the most basic, the most basic discontinuous functions there are. So we'll start focusing on very simple discontinuous functions. So the first ones we'll look at are called unit step function. And the unit step function is just a piecewise defined function, which is 0 up to a point, and then it becomes 1. So a unit step function is a piecewise defined function of the form where 0 for t less than tau, and then 1 for t greater than or equal to tau. If tau is 0, then we call the function u, and then in general, we therefore call the function u of t minus tau. So u of t minus tau essentially shifts our function to the right by tau. So instead of being 0 to the left of 0 and 1 after, this will be 0 to the left of tau and 1 after. So first, let's just consider the Laplace transform of the most basic unit step function, or of the unit step function. So if we want to take the Laplace transform of u of t minus tau, then we're taking the Laplace transform of the piecewise defined function, 0 for t less than tau, and 1 for t greater than or equal to tau. So we're taking the improper integral from 0 to infinity of e to the negative st times u of t minus tau dt, or the improper integral, or sorry, the integral from 0 to tau of e to the negative st times 0 dt plus the improper integral from tau to infinity of e to the negative st dt times 1 dt. So this first integral or definite integral is just 0, and the second one is fairly quick to solve. I need to give myself a little more space before I do so. Again, this first definite integral is just 0. And then we are looking at integrating e to the negative st. We would have negative 1 over s, e to the negative st. And then evaluating, I'm going to do sloppy form and just say evaluating from tau to infinity. So this becomes 0 plus negative 1 over s times 0. Right? As we let that upper limit go to infinity, e to the negative st will go to 0. And then we will subtract a negative 1 over s, e to the negative s times tau. And so we wind up getting that this Laplace transform of the basic unit step function, where we switch to 1 at tau, is just 1 over s times e to the negative tau s, or e to the negative tau s times 1 over s. Now let's move into just slightly more complicated piecewise functions. Let's consider piecewise functions of the form where 0 for t less than tau, and then f of t for t greater than or equal to tau. Actually, let's make this g of t. The entire piecewise function will be f of t. So f of t is equal to 0 for t less than tau, and g of t for t greater than or equal to tau. Note that f of t is just the unit step function evaluated at t minus tau multiplied by g of t, right? Because u of t minus tau is 0 all the way up to tau, multiplying by g, we will get that 0. And then u of t minus tau is equal to 1 for t greater than or equal to tau. And so we just have 1 times g of t, or g of t. So let's go ahead and now find the Laplace transform of u of t minus tau times g of t. So taking the Laplace transform of u of t minus tau times g of t, this is the improper integral from 0 to infinity of e to the negative st times u of t minus tau times g of t dt. U of t minus tau times g of t is 0 from 0 to tau. So we have 0 to tau for a definite integral, e to the negative st times 0, then dt. And then an improper integral from tau to infinity. U of t minus tau is just equal to 1 on that chunk. U of t minus tau times g of t is equal to g of t. So this is e to the negative st times g of t dt. This first piece is just 0. So we are simply left with a definite integral from tau to infinity of e to the negative st times g of t dt. And now we're going to do a little bit of a change of variable. So let's set u equal to t minus, let's not use u, we already have u's involved with our step function. We have ts, let's just use x. Let's set x equal to t minus tau. Then we have dx is just dt. We also have the t is equal to x plus tau. Our improper integral becomes a definite integral from 0 to infinity. Plugging in t equals tau, we do get x is equal to 0. Then we would have e to the negative s, and then t becomes x plus tau. So e to the negative s times, in parentheses, x plus tau. And then multiplying g of x plus tau, and then dx. Now let's rewrite this. We can pull out an e to the negative tau s out front. Left-hand side is 0 to infinity, e to the negative s times x times g of x plus tau dx. Now let's go ahead and rename our x back to t. So renaming our variable for integration. We can rename variables however we like. So I'm just going to relabel the x with a t instead. We get the integral, or e to the negative tau x times the integral from 0 to infinity of e to the negative st times g of t plus tau dt. This improper integral should look very familiar. This is just the Laplace transform of g of t plus tau. So we have e to the negative tau s out front, and then we are multiplying the Laplace transform of g of t plus tau. So we can take the Laplace transform of these basic piecewise functions. We just know that it becomes e to the negative tau s, whatever a shift was for a unit function was tau, multiplying by the Laplace transform of now our g shifted. So Laplace transform of g of t plus tau. So this is giving us the ability to now take Laplace transform of both sides, and then eventually we could translate it back with an inverse Laplace transform.